Hello, everyone. Okay, so whoops, here, let's see, there's a few chats. Hello, hello. So, um, somebody, let's see, I think Simon asked me last night in the email about the midterm. And, well, thanks for reminding me. How about if we have a midterm next week? I imagine that's when most of your midterms are. And I think it'll just be, you know, an exam where you can do it over a day. Like I'll give you a 24-hour period to do it so you can take as much time as you need. And I don't know yet, I guess, which day. I'll have to look. Probably midweek, end of the week. Does anyone have a preference for the day? Okay. It's really weird talking to you when no one talks back. Somebody should say something. Can you hear me?
I think would
Yes.
just next Thursday work?
Sure. So Thursday is the 11th. And I think I'll make it available probably from like whatever, midnight on the 10th, whatever, 12 a.m. on the 10th to 11:59 on the 11th. Well, I guess 12 a.m. on the 11th to 11:59 p.m. also on the 11th. So all day. Now, if I think, if you have like some kind of UDSS time thing, I'm not sure what to do in a case where I'm giving you a whole 24 hours. I wonder if they require me to give you 48 hours if 20, but I mean, it really should only take, a few hours, like an hour and 20 minutes or something to do. No thoughts. Okay. All right, last time we were talking about parallel OR, and this time we're going to talk about, I guess I got to share my screen. We're going to talk about the par statement, which is another statement which adds a kind of ability to do to have non-determinism in the language. I wonder. I'm thinking I should try to turn off my video, maybe, just so I'm not. Can I still share a screen? Yeah. Using up that extra bandwidth for nothing. Okay. So I hope everyone can see this. I thought I should be able to like zoom in more, but it's not letting me for some reason. Maybe I could look at it with a different tool. If anyone complains. Is this good for? Is there anyone that this is not good for? Can you read my? You know, you may have a little trouble reading my writing, but
No, that's fine.
okay. Okay, so you know, I might say that this morning we had a. So you know, I run the Wyoming Advanced Blockchain Lab with Mike Brofchek. So he and I direct the lab there, and one of my PhD students today gave a talk about the work that we're doing on the blockchain language, adding features to the blockchain language called Marlowe that was developed by IOHK, who funds, you know, a significant portion of the lab. They gave us $500,000 last year, and we got $500,000 from the state. The university had to throw in some funds, so we have like $1.3 million to run this lab. And we've got, you know, a number of students. If any of you are, you know, really interested in this stuff, you should send me an email, and you know, we could get you. Invite you maybe to some lab meetings. But anyway, we just had a talk this morning on not par or, but on setting up the small step semantics for the Marlowe programming language, and then setting up the semantics for the Faustus programming language, which is ours, and then proving that our evaluator actually does what it's supposed to with respect to the semantics, and proving that our compiler, I'll just put my video back on, proving that our compiler is correct with respect to the semantics. And so we're at kind of still, I mean, Marlowe is kind of a primitive programming language, really. It's implemented in Haskell, but we're trying to like add more features to it. We're not trying, we're adding more features to it so that you wouldn't have to actually know any Haskell to use the extended language, which we called Faustus. And so anyway, a PhD student gave a talk this morning, and he formally proved all these properties about that. I mean, some of the properties that he proved were that. So we wrote the semantics, and there's a way to formalize in logic these the exact style of semantics as we're doing here. And then we wrote the evaluator in a functional language inside this. We did all this inside of theorem proving environment called Isabelle. And then we're able to prove that the program that evaluates statements in the language together with a state to a new statement and a new state matches exactly what the evaluator does. So now we know the evaluator behaves like the abstract semantics. So now we're free to use the abstract semantics to prove other things. And so then we could prove that a kind of a standard thing to prove a compiler correct is to do the following, is to kind of prove the following theorem. Oh, I got to get my tablet going. Let's see. Okay, good. Turn on. And then where's my pen? There it is. And I'm just seeing if I have a available plug to charge it. All right, that's probably okay. So here, like if you have, you know, like let's say you have two languages, L1 and L2. And suppose, gosh, I wish I was better at writing with this. It's so embarrassing. My handwriting is actually not terrible. Languages L1 and L2, and suppose that P is in L1 and M is in, well, M sub I equals 1, 2. And P sub I also were I's in 1, 2. So choose a program P sub I that's in this language 1. And now we've proved a number of things, but like one of the things was if P1 in the small step semantics evaluates to P2, and then if I compile P1 to, let's say, M1, and then I run the small step semantics for M1, I get the same thing going either way across this diagram from P1 to M2. So if I start with the program in my language L1, and then I do 0 or more steps of computation to get to P2, well, if I compile, and then I compile P2 to get this program M2, I get the same thing if I take the original program P1 and compile. So you can think of this level as being like L2 as being like the machine code. Like think of it as being the JVM. And so this is some language, L1 is some language that's getting compiled down to the Java virtual machine. And you get the same thing. Now, what we have, either path leads to the same thing. So it means that the compiler kind of preserves the semantics of the small step semantics for L1 and the small step semantics for L2. And this means if you can prove this, which we did, we formally proved it in a theorem prover, this means that the compiler is correct. But we've also shown that, like, if I something like, so this is like the big theorem. This is the theorem that shows the correctness of the compiler. But there's other theorems that are like, if P1 is well typed, then, let's see, and P1 goes in 0 or more steps to P2, then P2 is well typed. So that means when you evaluate things, you don't break the typing system. And we also showed that essentially, I don't know the best way to write this down, but it's something like, that essentially the evaluator for this code, the evaluator for L1 is exactly the relation, this relation here. So it's something like, if eval star P, and actually there is a store, there's some state that needs to be done there, is equal to, let's say P1 is equal to P2. And that's true if and only if. So this means evaluate 0 or more steps of P1 and get back P2. That is true if and only if in the semantics P1 goes to P2. So this means that the evaluator for the language, so eval takes as input, elements from the language L1, so programs from the language L1 cross some state, and actually for us it evaluates to a pair, which is S prime. And this also takes a state. Technically, there's more. I'm trying to minimize the arguments here, but it's worth putting in. P1 comma S evaluates to P2 comma S prime. So eval takes a program and a state and evaluates to a program and a state. And remember that the big step semantics is a subset of configurations, which in this case are, well, we even had a slide this morning. I told them, make it so that the configuration, so that we put it into the same format as this class. I say, okay, show that gamma is equal to, for us, it's like Faustus programs. paired with a state going to, I'm sorry. This is just the configurations. And then the, if I move that out of the way, that'll be a big help to me. You can't see that thing, but it's blocking me up. So if our configurations are this, and then we define this by, is a subset of gamma cross gamma, and we define this relation inductively and in the theorem prover, and then, or you can think of recursively, it's like a recursive definition of this relation. And then our final, for us, the final state is always a contract that is the closed contract. And then, of course, it's paired with some state S. So they'll look like this, where so T is equal to close paired with S, such that S is an element of states. And so that's clearly a subset of this, because close is a Faustus program. So anyway, so the idea is that if I evaluate a program, well, and maybe the first way to, this proof is broken up into two parts, really. The first part is that if I take one step of evaluation of P1, I get to a new place, P2 and S, and that's true if and only if in the one step, big step semantics, P1S leads to P2S prime. So these are all things that we're doing for this contract, or, for this as research for this blockchain company. Blockchain code is a kind of critical code, like, millions of dollars or billions of dollars can depend on a smart contract being correct. So it's kind of worth expending the energy to do this kind of stuff to make sure that your compiler's correct. I don't know, any questions on this? Anyway, we had a talk this morning for an hour in the lab seminar series about this. I think a few of you in this class, I know a few of you are affiliated with the lab now. So we're glad to have, if you're a decent Haskell programmer and you like this kind of stuff, this is what we're doing. This is part of what we're doing in the lab. We also have lots of hands-on stuff related to designing hardware and proving hardware is correct and so forth. So does somebody has to say something. I mean, I guess in a way, I just want you to see that this is not like a bunch of abstract nonsense. We're actually able to verify the correctness of the compiler because we did this. In fact, I should say that we tried to verify something different to start with, and we couldn't do it. Everything just got too complicated. And what we did was, so this is the evaluator for L1, and then we have an evaluator for L2, and the form of the states are different, like this state here depends on the language. This is not, the state is not identical for L1 as the state you need for L2. So if I have an L2 evaluator, so if this is eval1 and I have an eval2 that has, woo, that is ugly. If I have an eval2, which has essentially the same type, but now we're using language 2 and a different kind of state. So it takes L2 programs paired with a state sub L2 and maps them to L2 programs paired with the state L2. And you might think that like you could do, okay, you start, if I go back to this, you start with P1 and you change these arrows. It's just, we've proved that it's identically the same because we proved that this arrow matches the eval, but this is just like saying, oh, that's the same as running eval1 from here to here. And this is the same as running eval2. And really, I probably should have made it clear that, this is, for L1, this is a small step semantics for L1. This is a small step semantics for L2. So you can see as you start to fill in the details, it gets more complicated, but this is about it. This is about the level of complication. So we started out trying to verify this without the semantics. We thought, oh, these programs are totally clear. It's only like 45 or 50 lines of Haskell. And we started trying to directly, essentially verify this without defining the semantics, the small step semantics for L1 and L2. And the problem is that when you needed to show some fact about the thing, you would have to unfold so much of the program. Like you'd have to unfold and look inside of each definition, and you'd unfold the thing, and what might be a few lines become like 50 lines more. So the whole thing is like 50 lines, but it's calling functions in there that are defined in other ways. So by the time you have to, if you find a piece of state that you want to get to that's actually changing in the process of the eval here or the eval up here, you have to unfold all this stuff, and you end up looking at this giant expanded program and trying to figure out, okay, this part changed, in going from here to here. And it was just too hard to figure out. So when we rewrote the thing so that we used the big step semantics that corresponds, like the theorems that we proved were, whoops, I didn't mean to create a new one, were that this is true. So that means our evaluator for L1 is exactly the same as the semantics for L1. And then we also proved that, well, we're proving right now that oh, that's a M. Okay, so we proved this theorem, and we're working on this one. The only one we needed really for the compiler was this. So we proved this. And so what we were trying to do before, so now we know that the small step semantics for these match perfectly the evaluator. So back on the previous diagram, we were unable to verify using the eval, but we can do it using the semantics because they're so much cleaner. Uh-oh, I do need to plug in. It's telling me the battery's low. On my tablet. Okay. So anyway, I don't know. Does, I guess it could be that this is like helpful because a lot of times I think I don't know, maybe more than half of you are always wondering to yourself, why do I have to know? What's this for? What good is this going to do me? Questions? Somebody has to say something. It's just not reasonable for me to have to like feel like this. I feel like everyone has to say something. How many people are here? Of course, now no one
I think
will.
it's nice to.
Go ahead.
I was just saying, I think it's nice to see the real life application to it. So it gives us some meaning of what we're learning is good.
Yeah, that's what I'm sort of thinking, is that maybe this kind of the application makes it seem more real. How many people here are seniors?
I am.
I am.
I am.
Few, not
I
that
am
many.
as well.
Not that many. I don't know. All right, I can go back to the regular lecture, I guess, if no one else has any other questions about that. Or all right, I'll tell one more like war story, which is that God, this is so long ago. How many of you were born were any of you born in 1988 or before?
No way.
You'd be really old if you were born in 1988 or before. But in 1988, I worked for NASA, and I had just gotten a job with NASA. And they sent me off to a meeting at the University of Texas at Austin. There was like a little spin-off company from that, founded by the Boyer-Moore theorem proving people. So some of you, or many of you, have used ACL2 in 3020 with Gamboa, and his advisor was one of them, but it was the other one who had the company. Well, I think both of them were involved in the company. And it was like this, it turned out to be like a historical seminal meeting in kind of system verification and design. And what they were doing was they had worked out, and a lot of this at that time, I mean, it was already kind of like understood that the way to verify things, even if it's not a programming language, you can verify all kinds of things using this kind of structure of like, okay, here's a higher level thing that's where the state representation is probably different from this lower level thing. And in this meeting, they had been funded by the National Security Agency, NSA, for like a number of years. And within NSA, they were kind of like, okay, we've been paying these guys a lot of money for years. Let's see what they have done and invite some other federal agencies that would be interested to come to the review. And somehow, I mean, I was about 30 years old, and I went down to this meeting, and I'm sitting at lunch in a very fancy, or breakfast at a very fancy hotel before the meeting starts, and these two guys at the next table are the guys from NSA that are funding them. They don't know who I am. They're going on and on about NASA's going to steal our resource and all this kind of stuff. So I'm sitting there all alone. I'm just like a 30-year-old guy, you know, first time I've traveled since I've been at NASA. I didn't even know really why they sent me to this thing. I went over and I introduced myself. I said, oh, by the way, I'm Jim Caldwell, the guy from NASA. And God, that was so funny. The NSA guys talking sort of out in the open public about, you know, their fears about what we were going to do. But anyway, what the ACL2 people, was actually, they had a really good name. They were called Clink, the company was called Clink, which was Computational Logic Inc. And what they had done is they had taken this kind of idea right here of this is oftentimes called, you know, a commuting diagram, because it doesn't matter if I go this way and come down, or I go this way and go across, I get to the same spot. And so they had worked out how to start. They had hardware designer, Warren Hunt, and they had an operating system guy, Bill Bevere, and I forgot what his partner's name was. And then they had implemented then after the hardware, they implemented a assembler language. So they had this, what they called the stack. And they actually had verified like does it not work when it's charging? No, it seems to be working, I guess. Okay. They had actually verified, like, at the hardware level, like a register transfer language, which is a very low level at which you can actually design hardware. And they had shown, okay, so, you know, RTL program 1 goes to RTL program 2 by, you know, an evaluation of the semantics of the hardware. So this is hardware. And then at the next level up, they had a language called Python, which was a assembler language. And they showed that when Python programs were evaluated on the hardware, the diagram commuted, that you got this. And then they wrote a simple, I forget what the name of this language was. It might have been actually similar to Pascal. I forget what the language was. So this was something like, you know, like a simple C language. And they defined formal evaluators for that. And they showed that that commuted, if you compiled the simple C into the Python assembler language, you got the same thing as, you know, going running the simple C program with the semantic evaluator for that, and then compiling. So this is kind of like running it on the hardware, and this is compiling the simple C program. And then a guy, Bill Vivere, wrote this amazing thing, which was an operating system on top using simple C. And he had proved, so this, what was the name? I can't remember the name of his operating system. And he had proved that according to kind of the semantics of the behavior of the scheduler and stuff, that when that was implemented, maybe he had simple C implementation. How did it work? Like, I'm not sure exactly what this top level would be. Maybe it was just an abstract semantics of like scheduling and stuff like that. And then he showed that when he implemented scheduling in simple C, that was correct. And then that was correct when it got compiled into Python. And then that was correct when it got run on this formally verified hardware design. It was really amazing. So this is like the Clink stack. And they actually got all this to work. This was a real amazing effort at the time. Computational Logic Inc. Oh, I guess it's not a K, it's a C. Now, the thing is that this is like the fundamental thing that we do in computer science at every level, right? You need, if you're talking about software engineering, you know, you maybe can think of this as a specification for the operating system, but then you have to implement it in this C language. And, you know, when you do this, what you're showing is that your implementation is correct, that it preserves the semantics. If you evaluate the semantics and then you compile, or you look at the code, you translate that into code, and you get the same thing as if you translate this into code and evaluate the code. And so there's this very abstract idea that, you know, we should probably be teaching, but we really don't. I don't think anywhere, which is what an implementation relation is. And it's basically that you can construct some kind of diagram, but it takes something else into account. And probably I should have looked this up before, because I'm sure I'm wrong. And it basically is like, it's almost, you prove a theorem that says basically the implementation. So we proved a theorem for our thing. We proved oh, it's on the next page. The if and only if version. We proved that eval behaves like the semantics, and that the semantics behave exactly like eval. So eval is no different. It's just a if and only if. But if you make it go one way, if you say eval P1S equals P2S prime, and if you said that implies going to the right, so if I got rid of oh, come on, don't get stuck to me. Okay, if I get rid of this and I prove instead that the behavior of this thing, and this is a theorem. It's like, oh, for every P1 and P2 and S prime, the following is true. If this implies that, then that shows that eval implements the semantics. Now, there's lots of different ways to implement the semantics. And I mean, we showed that this exactly behaves like the semantics, but there could be different implementations that imply the semantics as well. And that's what it means to prove that an implementation is correct, because you can think of this as saying that, this is like my specification of the behavior I expect. And this is eval is actually a piece of code. This is my implementation. So if you could prove the implementation so it's sort of like all the behaviors that are possible in the implementation, every one of those implies the correct behavior in the specification, then you've proved your implementation is correct. So we got a question this morning in the talk, and it was like, well, so what percentage of coverage, of test coverage, are you getting from these proving this? Can anyone tell me what percentage of test coverage we get? Well, I mean, if you look at the quantifiers, we're saying every possible program, P1 and P2, and every possible program state, S and S prime. So how does this relate to testing? If I prove this implies this, or if I prove even stronger, it's true if and only if, then what have I shown when I actually prove it? Don't be shy. Make something up.
Does it cover everything?
It covers everything. It's equivalent to doing, even though the states are infinite, there's an infinite number of, I mean, all right, maybe thinking, what do you mean infinite? Well, I mean, the state includes integers in it. So yes, we could have some bound, and we could say, like, except that in Haskell, you have unbounded integers. So like on any actual computer, you're going to have a certain size of memory, but it doesn't matter. This thing could blow out memory, but If it doesn't, if you have enough resources to run this eval, it has behaved exactly like this. So this is like every case. You have covered every possible. You don't need to do testing. Now, you might want to do some testing because, you know, you want to kind of exercise this thing before you start to prove it. You might try out the evaluator and see, okay, am I getting what I think I'm getting? I mean, I'm not saying you wouldn't need to test, but theoretically, you don't need to test if you got all this stuff right and you prove this. You got 100% of the test cases covered. This is why many of the big companies, well, first of all, the hardware, you know, at the time when this was done, which was 1988, so this was 1988, long before you were all born. There were some good restaurants in Austin, though, in 1988. I'm sure there's some good ones there now. I've been back very many times. So in 1988, when this was done, this was one of the first verifications of its kind. And and then there was kind of like a battle between the US and the UK, because the UK guys claimed they had done it first. And so then it got kind of like who did it first. And then there was like, oh, but it was all funded by national level agencies in the US and in the UK. So the agencies, including NASA. And so I got a good trip to the UK out of this, to go meet the guys who proved the thing over on the UK side. They got evaluated by the Clink people, and the Clink people said, yeah, but their proof of correctness of the hardware is really not good. Because, you know, because they had done it in all different, like in a kind of like a hodgepodge of different tools and different languages and everything. And this goes down to like a gate level design. Logic gates. And you can prove this. And then, believe it or not, I mean, you probably believe it, but you might not realize that there's levels below that, because, logic gates we think of as that's the hardware. But guess what? A logic gate is just an abstraction that's implemented in silicon that doesn't behave anything really. I mean, as a little unit, this box of transistors and things implemented in silicon behaves within the certain boundaries, right? So, I mean, what happens, if you're trying to implement like an AND gate, what you want to implement is like, you've got two inputs and you've got, true, true, and then P and Q is false, and then you've got true, false, and false, true, and false, false. And these are all false. Oh, this one's true. I'm sorry, I did that wrong. I was actually writing down NAND, which is a more likely thing to use in hardware. But so this is an F, and oh God, that's a T, and the rest are Fs. Where is this T and FF? Now, the problem is that down at the hardware level, what do you have? You have circuits. And the circuits don't have, like, really, the circuits are measured by voltage. And I mean, I don't know, it's been a long time since I really dealt with hardware design, and I can't remember exactly, but it's like, you know, you got like between 0 and 5 volts, and you say like, okay, you've got, you know, a range of so you think of this as like a wire, and it could be between 0 and 5 volts. And you might say, okay, false is equal to, like, but it's never exactly one or the other, or maybe it is, but it's not, doesn't switch instantly from 0 to 5 or 5 back to 0. So you might say false is like in the range from 0 to, you know, I don't know, 3.7 volts. And true is equal to 3.7, and I don't even know what to say here, 1 volt to 5. And so now down below here, there's like the physics of behavior of a layout in silicon. And so everything we build is stacked on one level on top of another. And what we do is we at, you know, the computer scientists basically say, look, I am going to accept the abstraction that you give me for logic gates. I don't want to ever go down and look down here and see, you know, oh, it's, you know, 0.25. I mean, getting this abstraction of logic gates to behave the same, you know, and so this is the outline plus the state, which would be the amount of voltage on each wire, and then this would be the, you know, the layout plus time cross with the state. And so, you know, all these have state in them. And but I never want to go down below here. There's a thing called SPICE that's a simulator that lets you simulate certain layouts of transistors. And you get to simulate what's happening there. You want your model to be that the switching appears to happen discretely, right? We only want to think about true or false or 0, 1. But they've got to deal with this. So what do you do if it's 3.70002? Well, then it's not 3.71, so it's neither true nor false. And so, like, the computer engineers have done an amazing job. It's completely, it really is a bulletproof abstraction. We never have to consider we just have to consider the gate level design. Well, and really maybe that's too low, although oftentimes we have to figure out how to run a register transfer language on a gate level. So to prove the correctness of ours, we might have to look at the gate. But if you're a computer engineer, you also have to go down below this and figure out, you know, how do you make a certain thing an implementation of a logic gate? And then the computer scientists never look, we never peel back the wrapper and say, wait a minute, you know, we never think that, you know, if you see something like this, you know, which is some kind of gate design, oh, I don't know, ores kind of look like that, curvy. And if you see some kind of gate design, you don't think that this thing doesn't work. You never think that. But that's because the computer engineers have done such a good job at making that an abstraction. You don't need to look inside of it. At the operating system level, for example, when you write your code, you never have to take into account that the operating system is running multiple processes at once. You know that you've got access to your memory allocated by the operating system, and if the operating system is doing its job right, your memory isn't like intermixed with the memory of some other program. You never have to think about that when you're writing your program. That's because having isolated memory spaces for individual processes is a good abstraction that works. So I don't know. Now we should have a little, I've sort of like gone on from this random thing in the beginning maybe, but not so random because it's what we're actually doing, to something else that I think, see, I was in, before I went to NASA, I worked for GE in a group that was doing hardware verification at the GE Corporate R&D Center in Schenectady, New York. And when I was working there, it was at this level and down to the transistor level, but not really so much. There were other groups working with the SPICE simulator and stuff like that. But it was just getting started. By 1988, this had been done, but there was still one little gap in the hardware design. One little thing that hadn't been verified that took years for people to figure out how to reason about properly and how to incorporate it in this. And that was like an asynchronous signal coming into the processor on an input line. And how do you deal with, asynchrony? Everything, once you get inside the hardware, you've got a couple of clocks and you're running everything more or less that is running, things are running synchronously is a good abstraction. So I don't know. Somebody has to say something. I want to hear what you think. Do you know this? That's one thing I could ask. Do you all know this? About these levels of abstraction that we work with, and it's our bread and butter in computer science, is building good abstractions. And then once you have them, you don't have to think about the details down below that. Same thing in network protocols, right? We don't have to worry about like the fact that networks are actually kind of like lossy, transport means like there's no guarantee that the bits that you send are the bits that are going to arrive, or that they're going to arrive, packets are going to arrive in the same order. But we have protocols that say, no, we can ensure that behavior. Like, it's amazing watching myself here. To me, it's just amazing that it works. I'm watching myself on Zoom. This is like so many levels of abstraction that are implemented to make this thing work. And a lot of it is incredibly complex technology that's going on. There's cryptography going on here, right between here. They're like securing the packets by cryptographically linking them. So wait, I have two comments. So Andrew is saying, Fuller saying, oh, privately, the hardware levels, I'm sorry, but it's not really that private. The hardware level's always interesting, similar to the benefits of the OSI model. There you go. The objects is another really good thing, but then you need to like say, oh, let's make a abstraction of a specification of the object level model so that we can talk about objects without worrying about some of the details of their implementation. All right, let me see. You know what, Tristan? I see you're a very good person because you have a photograph of yourself that shows, even though I don't see you, you and Colton are the only ones besides Letitia who puts up an L. And otherwise, I'm looking at a bunch of black boxes with names on them. So what do other faculty do? Does anyone ask you to speak? Tristan, tell me something, because I see you there.
So I actually have my picture there because that's what lots of faculty asked you to do if you don't have
Oh,
a face cam.
okay.
Just because I do understand for teachers, it is kind of off-putting when you're just staring at a wall of names. It's kind of
Yeah,
difficult to talk to text.
yeah. Hey, Jake. Jake just turned on his video.
S-
Hey,
Something
Tanner.
I've noticed, by the way,
Yeah.
um, is it seems like in a lot of these online classes, people are really active in the chat. And I know at the beginning of the semester in this class, a lot of people are active in the chat, but I don't think you can see it.
Well, I can't see it when I'm sharing my screen for some reason, and there may be a way I can try to fix that. Okay, that's a good point. But let me ask you, Tanner, have you seen this idea of these layers of abstraction in any other
Um,
class?
I think I don't remember the name, but as far as like the internet goes, I think I saw it in there. Like how you don't worry about the lower levels of.
Hmm.
Um,
Yeah, so that would be
I feel
like
like I'm not being.
networks. Yeah, probably. I don't know. Maybe they cover that somewhere else. One of the things that was a hot topic, I mean, people wrote papers about this. They had said, like, okay, what's better? And I apologize to the women here, but at the time, in 1988, it was mostly men doing this. They had like what they call the tall, thin man versus a stack of short, fat men. And what the short fat man was like an expert at his level, like an expert at the hardware level. Then above that was an expert at the, programming languages level. And there was an expert at the operating system level. And so sort of at each level of abstraction as you're going through, and they're not always stacked perfectly well like this, but sometimes they're parallel. You have one person who really knows everything about that area, but the tall, thin man was somebody that knows something about all of them. And it was like a big question for companies like, Motorola or Intel or whatever to try to figure out, like, how do we want to train our people? Who do we want to hire? Do we want to hire a bunch of thin men or a bunch of fat men? It was like a big issue, like which is more effective in a team? And usually I think you probably need a thin man who understands the whole thing and a bunch of fat men. Or, a thin person and a bunch of fat people. But gee, that doesn't sound that good either. You can probably figure out that I think that model of the tall, thin man versus the short, fat man was probably made up by someone who was a tall, thin man. It sounds so much more appealing. But one of the things that I always thought from this was that a saying that became kind of my mantra for a long time is, well, and still is in a way, is that one person's ceiling is another person's floor. Like, the person who's writing application code does not look inside the compiler. A compiler forms a layer of abstraction, And people who are using programming language compilers assume that when they write code, it's going to actually to compile something that is what they understand the code should do, according to their understanding. Now, sometimes you can have the wrong understanding, the compiler's doing the right thing, but you still don't want to think about the compiler. You assume, in fact, if your code doesn't compile or if it does the wrong thing, then you wrote the wrong program. At least you assume that until you discover a compiler error. And then that's kind of like the end of your career, because then you don't know what to do. Every time there's an error in your code, you think it's the compiler that that did it. Once you see it once in the wild, that's it. You always assume that's what's going on. At least that's what happened to me for like a few years. I had a compiler error. I finally tracked down the error and the bug in the compiler, and then for years after that, I always thought it was them and not me, until finally I realized, like, no, actually compilers work. I was in some ways maybe lucky to find a compiler error. But so in this other stack, in the areas where it's more like a stack, but even in that area, it's kind of like the compiler writer is looking up to like a specification of in an ideal world, there's a specification of what the programming language does that the people learning the programming language read. And then the compiler writer is implementing that programming language by translating the programming language down into assembler code. And so that's kind of like a good example where, the compiler writer is looking up at the specification for the programming language, but for the applications programmer, the specification of the programming language is the floor of what they look down, they see that, they don't want to look past that. And that's where good you have a good abstraction when people don't really have to look down. I mean, the only reason that Zoom can work is because of this partitioning of functionality into various abstractions, and then being able to implement those abstractions so that they behave as they're expected to by the other abstractions that are depending on them. And so that kind of decomposition of a problem into something that can be handled by a human, like if you said write Zoom from scratch, you couldn't possibly do it. No one could. The only way we got here was by like 50 years of computer scientists working on designing good abstractions. This is a good thing. Like you often feel like, you'd like hear from engineers, like you might go get a job. Let's say I worked almost my whole career. Even now, I'm a computer scientist in an engineering organization. Now if there's any engineers here, I'm liable to piss someone off, but whoops, maybe I'm not supposed to say that. I'm going to make somebody angry. But, it's like there is a kind of a sense among engineers that we can write. Well, I've had them literally ask me, a head from another department when I was department head, we write a lot of programs. What do you guys do in computer science? It's like, what? We've made it possible for you to write programs. Like 50 years of compiler development and programming language development and abstractions like object-oriented programming, and the list just goes on and on and on. And like if you didn't have good solid abstractions, like right now everyone thinks they can program because they can write a Python program, and Python probably, again, it may not be the ideal solution, but it is a kind of a solution that a lot of people can learn. And that evolved after you couldn't have implemented it 50. I know it seems crazy to talk about 50 years of computer science, but we've really had more than that, really. I mean, if you take like the 1960 to be about the beginning of the first compilers were written in like fall of 1959. So John Des Enfants, you showed up as a photograph. What do you think? Say something. Thank you for the photograph.
Yeah, I'd put my photo on before, but then I guess it must have logged out and I never could figure out where it disappeared to, but
Uh,
I just managed to get it back on since we were talking about that.
okay, Letitia says she thinks a lot of this was covered in computer organization, and it's true.
The
But
levels of abstraction thing like 10 minutes ago,
yes, right. Levels of
if you had
abstraction.
read the chat.
Yeah. Well, but I mean, that's the entire thing I've been talking about almost all day. And I guess we're going over now, but I just go back and share just as, you know, you're leaving what the talk on programming languages talk was today was these are two different levels of abstraction. M1 and M2 are like, to us, an assembly language. And for our higher level language, we compiled down to those. And the only way we could really make it work was by defining the semantics, because it simplified the statements of the theorems and also gave us like immediate access to the to the values that were sometimes hidden multiple levels down in the code inside of a data structure containing another data structure. It all comes to the top. So anyway, all right. Well, this is like a lecture on the practical application of this kind of technology. And, you know, if you want to talk about it more, we could, you know, we can talk about this some more. You know, you can, I have in the past described like the semantics of the asteroids computer game, and then, you know, you build a little implementation and then you prove that it's correct with respect to the semantics. And so the semantics are easy to describe. Oh, okay, you know, you push the left button and the thing rotates, the spaceship rotates left, and so forth. Anyway, you can use this technique to write really good software in anything you're doing if you think of your problem as really being this. Somebody's told you, I want something implemented. So maybe they're telling you at this level and you implement this level, but you want to show that you implemented what they asked for. And you can show it if you can prove this kind of thing. And maybe you can't formally prove it because you have to be kind of sophisticated in logic and stuff. But if you think about it that way, you're going to design better software for sure. So anyway, all right, I'll let you go. I'm sorry. Wow, I went over again, even today. All right. See you later.
See ya.
Yeah, go ahead.
Thank
So,
you.
basically the abstract syntax is the same as semantic equivalence. Like it'll just all compile down to do the same thing.
It means it's semantically equivalent. It means that the compiler has translated this higher level thing into a lower level language, and the behavior of what you expect from the evaluation of the code up here is exactly, the compiler did exactly the right thing, because you can do that, make that diagram commute. You can say, evaluate my program and I get to a certain spot with the abstract semantics where I compile it down and I evaluate that program and I get to the same place as if I went over and compiled or if I compile and go over. And that shows that the two are essentially identical. All right, I better run. I actually have to go to town for something. All right.
See you.
See you.
Yeah.
Bye.